we are going to continue our study of the space-time algebra using this wonderful paper, and we have made a lot of progress. We have gotten all the way into section 3.62 paravectors. Today we are going to finish paravectors and hopefully begin, or maybe even finish, relative reversion. So let's begin. Now we left off last time with this new form of expressing a multivector. And it involves only paravectors with a bunch of scalar parts and a bunch of relative vector parts. They call them vector parts, but we got to be careful now. Vectors meaning at least three different things, right? Vectors are the four vectors of special relativity. Vectors are the proper vectors of the algebra, and now vectors are relative three vectors. So if you just say vector, and there's actually a fourth one, right? Anything in a vector space is a vector. So any member, any multivector is also a vector, right? So the vector is like the most overloaded word in this mathematical physics language. I'm absolutely convinced of it. I can't think of another word that can have that many meanings. So let's understand what we're after here. We're talking about relative three vector parts, because you see these arrows in this paper. When you see these arrows, you're dealing with relative three vectors. So we've learned about this new partition, and which is now manipulated the way we can get with only two things. The way we can get away with only two things, a bunch of scalars and a bunch of relative three vectors, is by using these duality factors. Everything's related in the geometric algebra through these two dualities, in the space-time algebra to be specific, through these dualities. So let's have a quick look at how we got here. So remember that a multivector M, this is the way a multivector M is expressed. You'll see that this is the scalar piece right here, right? And the vector, there's the vector basis, right? And this guy here is a vector in the multivector. And it is we're going to call that a proper vector. But it's a bunch of components. It's a four-dimensional vector space in its own right. And it's got four components. And there it is, right there. Then the same can be said for the bivectors, right? The bivectors are all right here. And the bivectors, they can be expressed in they have six basis vectors: gamma 1, 0, gamma 2, 0, 3, 0, 2, 3, 3, 1, and 1, 2, where I'm choosing the basis vectors from the paper. And I'm pretty sure that the way they did it is they went with gamma 1, 0. Now we know why they chose gamma 1, 0, 2, 0, and gamma 3 zeros, because they want to use the benefits of sigma 1, sigma 2, and sigma 3 later. So that explains why they choose these as our basis vectors for the general algebra. And these guys here, if I'm not mistaken, should be sigma 1i, sigma 2i, and sigma 3i. They should be the duals of them. Actually, I think they went with this, though. I think they went with the inverse dual, the inverse dual. Regardless, though, the paper chose it, and it's convenient for whatever that reason is. The key point being they definitely chose these to be so they could use this relative basis vectors. So there are all the bivectors right there. And then the trivectors are likewise constructed with component, and there's four trivector basis vectors, right? 1, 2, 3, 4. And then ultimately there is one pseudo scalar basis vector. So every multivector can always be written like this, and this is where our geometric algebra, any geometric algebra, has that structure. And just to simplify it, we say scalar, vector, bivector, trivector. And here we allow ourselves, instead of coming up with another symbol for the pseudoscalar, like we could have come up with some weird symbol, like if we use Greek letters for scalars, we could say we use maybe some sort of Hebrew letter for pseudoscalar. I don't even know what a Hebrew letter looks like. I mean, maybe we would use, say, I don't know, some weird little hieroglyphic, right? that would look like, some sort of, that symbol would be a pseudoscalar, right? And but we don't do that. What we do is we allow ourselves to throw down the pseudoscalar basis vector as I, and then allow beta to be a real number. So this first step is actually a bit of a simplification from this overall general massive representation in the full basis. We allow ourselves to borrow a real number and multiply by I and call that product a pseudoscalar. Right? So we're already using a duality relationship right in the beginning, because that pseudoscalar is clearly the dual of a scalar. So we're exploiting duality even in this early stage of writing down a general multivector symbolically like this. But then we kind of go long on this and we say, but there's another way of organizing it. We can take the scalar part and the pseudoscalar part and bind them together into a complex scalar, and we can take the vector part and the trivector part and bind them together into a complex vector. And so in principle, we could write this as a complex scalar z plus a complex vector, which we might call bold v, plus a bivector, right? And so that might be yet another way of writing down a general multivector. And all that is just rearranging the order of these guys and getting rid of trivectors and in favor of duals of vectors. So we always need now a vector W, and its dual will be a trivector, but we're now going to wrap all of these trivector basis vectors up into duals of these basis vectors here. So that's another way of tightening up our work. But then we can go even farther and we can say, oh, if I know what gamma 0 is, right? So far, everything above this line, that's all proper, right? That means it doesn't matter at all what reference frame you're in. But below this line, it does. Below this line, I do need to know what reference frame I'm in, because I'm going to now take this vector and I'm going to split the vector up into a relative 3 vector and the dual of a relative 3 vector. And I'm going to distribute that into these two parts. So actually, oops, wait a minute, that's not right. Scratch that. I'm taking the bivector, right? The bivector. I'm taking the bivector and I'm splitting it up into its relative 3 vector part, and the part that's left over is the dual of a relative 3 vector. So I need to find two relative 3 vectors, one of which absorbs the first 3 basis vectors, right? So the first 3 of these actually end up landing here in E, and then the last 3 of these have to land in BI, right? BI, but I have to make sure that the basis is correct, right? So I'm using, but I need to know what gamma 0 is to do this, right? Because I need to be able, this split is very dependent on gamma 0. If I don't have gamma 0 down, I can't do this split at all. So what I've basically gone is I've taken this bivector now and split it in half. But you'll also notice, though, this does not include the complex. This isn't progressive, right? I've this complex formulation, I've left it behind. Because here, you see I have alpha and beta I, but here I is all over here. So I've sort of separated beta I from alpha in this kind of expression. So all I've done here is I've used our gamma 0 and broken up the bivector into a relative 3 vector and the dual of a relative 3 vector. And then the last step is we went really long on that. And we said, well, I've already taken this bivector and I've split it up. Well, how about now I'm going to take this vector and I'm going to split it up into a paravector right multiplied by gamma 0. That's exactly the same thing, right? V, the proper vector V, is some paravector right multiplied by gamma 0. So it is the relative dual of this paravector. And we defined a paravector as a scalar plus a relative 3 vector. So this is getting really fascinating because we're getting closer to things we actually use in regular physics, right? In regular physics, we use electromagnetic field vectors. We use magnetic field vectors. We use momentum vectors. And then delta is the time component of a momentum 4 vector. This object here is the geometric algebra or the space-time algebra equivalent of a true 4 vector of regular space-time calculations. Well, actually, I got to say no. I think this proper vector is probably more the space-time algebra equivalent of a regular 4 vector. This is when you're trying to do special relativity without 4 vectors, right? You would have something like this. You would have a time piece and a vector piece, and you have to keep track of how to keep them all together. And but likewise, this pseudo vector, right? That's a pseudo vector right there. Well, I take the vector piece, the dual of that pseudo vector is W. I take that and I break it up into its paravector part with right multiplied by gamma 0. And of course, I just floats out on the far right side. So this whole product here is where is the migration of omega I or gamma wi goes to this new paravector time the dual of this new paravector times I. Phew. So you can look at all of these things, and this is about as far as we can go. But now the difference is, of course, these two, and this one in particular, is fully determined by your reference frame. If you don't have your reference frame locked down and chosen, this split is hard to do, or you can't do it. But what's important to really understand isn't so much that, it's that this partitioning completely depends on gamma 0. So if you have a different reference frame with a different gamma 0, every one of these components is going to change. Well, that's actually not completely true. Alpha won't change, for example, and E won't necessarily change. Alpha will change. We're going to go through this in detail, actually. Alpha won't change. E will change because, remember, that split for E depends on gamma 1, sigma 2, and sigma 3, and each of those depends on gamma 0, right? That's gamma 1, 0, for example, and gamma 2, 0, and gamma 3, 0. So if you change gamma 0, you're going to change those basis vectors, which means you're going to change E, right? So E does not necessarily change. E does necessarily change. Sorry, E does necessarily change. But A is the only thing in this whole list that isn't going to change at all. In fact, let's go through that. I think that's the next part of the material. So let's look at how these things depend on gamma 0 and also how they depend on the handedness of the reference frame. In fact, that's the next topic of the paper. So we've got this fully frame-dependent form. Usually when you see frame something, it's always frame-independent, frame-independent. Frame-dependent now is what we're talking about here. It's all frame-dependent. So we've broken everything down to a bunch of scalars and a bunch of 3 vectors. A bunch of scalars and everything in here is a scalar or a 3 vector, right? Gamma 0 and I are these duality factors now. You think of them more as duality factors. So, but scalars and 3 vectors, so we've kind of really, we've used the dualities, the 2 dualities we have. There's this relative space duality, relative frame duality, and this Hodge duality as fully as we can to decompose M into this form. So the appropriate duality factors, right? These paravectors are the quantities usually considered in frame-dependent treatments of relativistic systems that use traditional vector analysis. And that's true. Traditionally, we choose a reference frame and we do all our work in a certain reference frame. because it's intuitive and it involves a little bit more elementary math, and you certainly don't need to learn space-time algebra to do it. I suppose arguably we should teach space-time algebra earlier in the curriculum, and then you would use space-time algebra to do it. But I can't imagine a world where that's the way it's done. But that might just be because I'm so entrenched in the world that I developed and trained through. So it's hard to know how younger students are going to think in the future, right? Anyway, these paravectors are quantities usually. However, the geometric origins of the quantities involved become obscured when they are lifted outside the space-time algebra. So we're going to talk about that a little bit. We can recover in this paragraph. We can recover some distinguishing information about the scalars by examining their behavior under frame transformations and spatial reflections, which we summarize in Table 6. So let's have a look at that. That's what I was doing a moment ago. Let's consider alpha, right? If I were to change gamma, right? If I were to change gamma 0 to gamma 0 prime, that is a frame transformation. I'm going to a new frame where it's where the stationary observer has a different relative state of motion than the stationary observer in the first frame, right? But if I do that, what happens? Well, this gamma 0 will be changed, right? It will be transformed. We're going to have to transform that gamma 0. And there's a gamma 0 hidden in there. And this gamma 0 changing affects those two. And this gamma 0 changing certainly affects this term. It definitely affects that. There's a gamma 0 buried in here, right? There's a gamma 0 buried in here. So, but none of those gamma 0s are going to affect this term over here. So alpha doesn't change. If you change frames, alpha doesn't change. So that's kind of interesting. And what does it say? The scalar alpha is invariant under frame transformations and spatial reflections, so it's a proper scalar. So what about spatial reflections? Well, spatial reflections are introduced wherever you see gamma I, where I is not 0. So spatial reflection definitely affects this I. So everything in here is affected by spatial reflections. This guy, its basis vectors are based, sigma I always has a gamma I, gamma 0. So spatial reflections affect E. And the point is it doesn't affect, there's nothing that affects A for spatial reflections, because that's what they're talking about. The scalar A, you don't see, if you change gamma I, A remains unaffected, is the point. So frame transformations are what we're going to call changing gamma 0. So this is related to gamma 0, and spatial reflections are related to gamma I. So it's a proper scalar. The scalar B flips sign under spatial reflections but does not change under frame transformation. So it is a proper pseudoscalar. So I think the way to understand this is you go up to beta here, right? And let's look at where it sits in this big picture. Well, ultimately, beta's real representation is beta I. Now, when you do a frame transformation, I never changes. I is sort of a constant thing. It's a frame invariant idea. However, if you do a spatial reflection, right? If you do a spatial reflection, what's going to happen is, remember, this is beta. A spatial reflection, either one or all three of these vectors are going to change. And so I is going to change sign to minus I, right? So the beta I piece, that's the part that is the true pseudo scalar, and it changes under spatial reflection. But if you transform all the components together, you're just going to end up with gamma 0 prime, gamma 1 prime, gamma 2 prime, gamma 3 prime, and beta, the number beta, won't change. So The scalar beta flips sign under spatial reflections but does not change under frame transformation. It's a proper pseudo-scalar. We call it a proper pseudo-scalar. Then you say, all right, well, let's look at all the rest of these things, right? Now, the game is to understand how all of these different pieces transform in different ways. And delta is invariant under spatial reflections but changes under frame transformations. That's delta here. Well, delta is a scalar. There's no multiplication by any of the gamma i's, but there is gamma 0. And if gamma 0 changes, then it's going to affect delta. So it changes, is a relative, so they're calling this now, this is a sort of a new word, a relative scalar. That's a new word, but it's easy to understand. It is the time part of a 4-vector, right? So it is the time-like part of a 4-vector. They're calling it a relative scalar. And sure, that's exactly what we understand to be delta rho, right? When we write this paravector in 4-vector form, it looks like delta rho. So that's easy. Then the scalar W, now more obscure, pseudoscalars are already pretty obscure, right? This beta is already a little bit of a weird thing because it doesn't really show up in elementary physics. You don't see it much. You see plenty of scalars out there, but you don't see a lot of pseudoscalars. They do exist, in particle physics. You have pseudoscalar type particles, but in electricity and magnetism, a pseudoscalar would represent a magnetic charge, which we presume is 0 in elementary magnetism. The scalar omega flips sign under spatial reflection and changes under a frame transformation. So it is a relative pseudoscalar part of a 4 pseudovector. So that's this guy here, right? Well, that gamma 0 is what drives its change under frame transformations, and flipping the sign of any one of those spatial directions or all three will give you its parity, right? So it changes parity. So that's all good. And likewise, you can do the same. You can play the same game with with the bivectors, right? This clearly will change sign under a parity, under a reflection, because it has gamma i's in it, right? That we've already discussed how a full vector, how E, which is dependent on sigma 1, sigma 2, and sigma 3, those all have gamma I zeros in it. So you start screwing with gamma I, you're going to screw with E. So E changes sign under reflection through the origin. B itself, all alone, so does B. But the quantity Bi, the two reflections cancel, right? The reflection in I will cancel whatever reflection is in B. And so ultimately the quantity Bi is a pseudo 3-vector. And you combine that with beta and you get a pseudo 4-vector, right? And then P, which is a classic example that they're trying to signal here, is momentum. Momentum clearly changes under a frame transformation, but momentum also changes sign under a parity flip. But this thing A, for which they don't have an example, but I think they're trying to lean into angular momentum here, will change with a frame transformation and will not change under a reflection, a spatial reflection, because the change in I will cancel with the change in A. So reading on, we can distinguish 3 vectors by looking at spatial reflections and transformation properties. The vectors E and P flip sign under spatial reflection, so they are polar 3 vectors, but B and A do not flip sign under spatial reflections, so are axial relative 3 vectors. However, while the combination of components delta P transforms as a proper 4 vector and omega A transforms as a proper 4 pseudovector, the combination, of the components in E and B, so if you take all of the bivectors, it transforms as what is usually considered as an antisymmetric rank 2 tensor, which is a bivector, as we indicated in 3.1. So we've already talked about that, right? That E and B together are just one big bivector. And as being a bivector, it's got all the antisymmetric properties of a rank 2 tensor. We did that. We discussed that a few lessons ago. For convenience, we summarize the various expansions of general multivectors in Table 7, comparing the proper expression of 3.7 to the frame-dependent expression of 3.47 makes the geometric origins of all these transformation properties clear. So what they're saying there is, what are they saying? This is the 3.7, right? If you look at all these things, this is the straight geometry, right? This is little pieces of volume, little pieces of area, little lines, a point, and a little pieces of hypervolume, right? And so you take this stuff and you compare it to this, just like we did, and now we can say, oh, the reason that, E is a polar vector is because it's a relative 3 vector built off of these little planar objects. And that's how it works, right? So this is where we sort of attach geometry to the things we knew in standard physics, is by understanding this, and by understanding this is the geometry actually lives in here ultimately. I'm pretty sure that seems to be what they're getting at. The proper combinations of relative quantities correspond to distinct geometric grades of a space-time multivector, right? And so the proper combinations of relative quantities, what they mean there is they mean things like T and I guess X is a good example, right? T and X. This is a combination of relative quantities that really forms a proper object X, right? So they correspond to distinct geometric grades of a space-time multivector. So this is a grade 1 object, despite the fact that this combination is a grade 0 and a grade 2 object, where we know that they're related to this grade 1 object through this duality transformation. So that's what they're saying there. And the geometric structure is left implicit in standard vector tensor analysis methods, even though the transformation properties remain. So the space-time algebra makes this structure explicit, intuitive, and easily manipulated in calculations. So what I think they're getting at there is that if you look at this, right, if you're working just in our classic elementary physics, if you're staring at elementary physics, you're looking at scalar objects, you're looking at things like alpha, you're looking at electric fields, you're looking at just magnetic fields, right? Just the magnetic field. You're not this I is not part of it. It's just a magnetic field. You're looking at momentum vectors, or if you're doing somewhat intermediate work at least, you're looking at least the momentum 4 vector, right, p mu. And nowhere are you really looking at pseudoscalars. But with all of that, you have to remember, this is a polar vector. This is an axial vector with these. Maybe I'm giving it this arbitrary little signal. This is a invariant scalar. This is a pseudoscalar, right? And but we don't tag it with these singles. We just have to remember, right? Now what they're trying to say is, no, you don't have to remember anymore, because this structure here is really designed just to make contact with the world that we've worked in and to see why things are the way they are. Fair enough, right? I mean, that's sort of the point, I guess, is to make contact with this abstract Clifford algebraic structure with the regular physics that we use. And this statement right here is that connection. All right, so I like that. What next? After all that writing I just did, the paper, of course, has a beautiful chart because they understand how important this is. But the graded form, that's what we, and the complex form, and the relative form. All of this is fully embedded in the space-time algebra. And if we had done the historical stuff, we would have seen that, historically you were dealing with these quantities, and there was a historical trend to use these quantities in the past. And so it's just kind of interesting to see how this is all laid out. But this gives you a nice complete list of all of these things, the pseudoscalar, the relative axial 3-vector part of X, right? So the only thing I want to call attention to is this part here. Like, let's look at B. B as written right here, right? The expectation is that B equals B1 sigma 1 plus B2 sigma 2 plus B3 sigma 3. So if you just look at B as literally written right there, forgetting about this I, it is a relative 3 vector. And a relative 3 vector, just like this E here, does it all by itself is mapped into our physical space as a polar vector. So this B here, as written, is really a polar object in the sense of how it handles itself under reflections. I'm not quite sure why they didn't write BI here to capture the axial nature, right? Until you multiply by this I, the axial nature doesn't become apparent, right? So, but I think what's going on here is what they're trying to say is that when you work in regular physics, you deal with a magnetic field B that looks exactly like an electric field E, right? There's no mathematical distinction in the way these quantities are written down and worked with, right? They are the same type of vector. There is only one type of vector in regular three-dimensional Gibbsian styled geometry. But we keep in our little pea brains, but remember, B is axial, not polar. So we carry that around with us in our brains. So I think that's what they're trying to get at here, is B is what we normally think of in regular physics as an axial 3 vector, right? But it's the relative axial 3 vector part of F. Well, F only has one relative 3 vector part, and that's E. The axial 3 vector part has to refer to BI, right? So I found that a little confusing. I'm not sure. Maybe there's some other way of understanding this, but just keep that in mind when you look at this. So now they're going to introduce a new concept called relative reversion. So let's study that relatively quickly. I don't want to get bogged down in this one too much, just because, it's sort of obvious now. I mean, these things shouldn't be too hard to see. I don't think we have to do an example of every single thing anymore. But this symbol that we normally use in physics for adjoint, they use for, in this paper, relative reversion. Now, sometimes, be careful. I've seen papers use the dagger for reversion, straight reversion, right? And I've seen different symbols for reversion. I've seen even other symbols for reversion. But relative reversion, you don't see, not a lot of papers, there are papers that don't even mention relative reversion. But let's get a handle on it. Relative reversion is simply reversion both right and left multiplied by gamma 0. So if you were to take our favorite new completely relative form of M and execute relative reversion, you would just see a couple key sign flips. You'll see a sign flip here, a sign flip here, and a sign flip here. So the relative 3 vector part of both sections, of both partitions of M, changes sign, and the pseudoscalar and the pseudoscalar and the pseudo vector, or I guess the dual relative vector part flip sign. So, I guess we could work that all out, but just remember, you got to move this I in here because we're taking the relative reversion of the entirety of M, right? Well, so for example, let's work out this one. So we consider beta I, which is beta gamma 0, 1, 2, gamma 3. We take its reversion. The reversion of this whole thing is beta gamma 3, gamma 2, gamma 1, gamma 0. We just reverse each one of those. Then we slap 2 gamma zeros on both sides. This guy squares to 1, so that goes away. And then I count 1 flip, 2 flips, 3 flips, and 3 flips. And so you get a minus gamma 3, 2, 1, 0. And I equals I reversion. And this is I reversion here. So it's just minus beta I. So beta I goes to minus beta I under this operation of reversion and pre and post multiplication by gamma 0. So that's where this negative sign here comes from. And you can do the same for beta yourself. Right? So you can kind of work all of these exercises, and it's a good training, right? Prove to yourself. This is like, I don't give homework in this thing. I just assume you guys are struggling with this at the level you care about. But you should be able to demonstrate each of these negative signs by just the similar work that I had just done. So if we compare with 3.47, where's 3.47? What was that? So 3.47 is just our expression for the fully relative form of a multivector. That's what 3.4. So without these sign changes, right? So I guess we're going to compare. They want to compare the relative reversion of M, which is gamma 0, M adjoint gamma 0. They want to compare that with this. And let's see, we should see a minus sign here. Let's see if I've memorized this right. We put a minus sign there, put a minus sign there. I think those are the 3 places that we showed it. Let's see if I got that right. So we're comparing this with 3.47. We note this gamma-dependent involution has the effect of proper complex conjugation for the complex scalars. So, but the effect has conjugation with respect to the space-time flip for the complex bivectors. Okay, so first of all, gamma-dependent involution. Well, clearly this is gamma-dependent, right? If you have different gammas, this process is going to change if you change reference frame. So it's a gamma-dependent involution. What's an involution? Well, if you do this thing twice, right? If you go with M dagger, dagger, what'll you get? You'll get gamma 0, M reversion, gamma 0, and then you'll have to reversion the whole thing, gamma 0, gamma 0. And the reversion of this guy inside is going to be, it's going to go gamma 0, M reversion, reversion, gamma 0. So it's going to go gamma 0, M double reversion, gamma 0. That's because the double reversion, or the reversion of a vector is just a vector, right? And then you have gamma 0 out here. And so these gamma zeros combine to give you 1, so you have M reversion, reversion, which equals M, right? So that's why it's an involution, right? It's an involution because repeated application returns what you have. Somebody asked in the comments, what's the difference between an involution and something that's idempotent? Idempotent, right? Right? There's a difference, right? Involution and idempotent are the same, are different. Idempotent means if you apply it once and you apply it again, nothing happens. So if I have an operation on X, OX equals Y, but OY is going to equal Y again, right? And forever. So you apply it once and it never changes. That's my recollection of what idempotent is. So what it's saying here now is that this operation of relative reversion on a complex scalar is the same as complex conjugation of the scalar. Okay, fair enough. I mean, it's pretty easy to see. We know that alpha doesn't change, and we know that beta I does change, so that makes sense. But it has the effect of conjugation with respect to the space-time split for complex bivectors. So if you take a bivector, f, right, f is always going to be split into this relative 3 vector plus another relative 3 vector's dual, right? They're saying, oh, this relative reversion is going to change the sign of this thing, right? Okay, and so that's pretty easy, but that's not equal to f conjugate, the complex conjugate of f. And this point is a little bit subtle because the idea, remember, the idea of a complex conjugate of a bivector, right, was f equals its canonical form times e to the I phi, right, where this has a fixed signature of -1, right? So the complex conjugate of f is equal to f e to the minus I phi, right? And what they're saying is that obviously this is proper in the sense that it doesn't change with reference frame, but this thing here, right, this space-time split does in fact change with reference frame. Now, if you go back to the complex scalar, right, what saves that? Well, why is it that the reversion of the complex scalar does in fact equal its complex conjugate? Well, alpha and beta, as we learned before, are unaffected by frame transformations, right? So these two coalesce to be the same in this case. In this case, they don't coalesce, right? Because you've got the space-time split is totally frame dependent. And then this vector case is somewhere sort of in between, I guess. The relative reversion of a 4 vector only flips the sign of the relative 3 vector part. So you actually have to take your 4 vector, write it in this relative form, right? You take this paravector, you write it as the form of a dual of a paravector. That's what's going on right here. And then you take its relative reversion, and the relative reversion of this object will just flip this one sign. I guess we could work that out. Actually, this is a good exercise. I just ran through it, but we're looking for delta plus p, this paravector, the dual of these, relative dual of this paravector, adjoint. So we're trying to solve this expression right here, right? So we run through the definition, right? So we pre and post multiply by gamma 0, and we take the full-on reversion, right? And the full-on reversion is going to put gamma 0 over here, and then gamma delta plus the relative vector p will go on the right, but we have to reverse vector p. Remember, as I keep saying, the relative 3 vector p is a bivector, right? So being a bivector, it has a reversion, right? The proper vector p, its reversion is equal to itself. So p reversion equals p. But the relative 3 bivector, its reversion is actually significant because its basis vectors, sigma 1 equals gamma 0, gamma 1. Well, the reversion of that is the reversion of that, which is gamma 1, gamma 0, right, which changes sign. So with that in mind, we got to do this whole reversion. So here's the left geometric or space-time product with gamma 0, the right space-time product with gamma 0. This is the reversion, so I've got to calculate the reversion of p, but I just showed you that each of the basis vectors, sigma I reversion, is going to equal minus sigma I. So you immediately get this sign flip. I took these two gamma zeros together and squared them to 1, so you don't see it anything on the left. And then I distributed this in from the right, and I got delta minus p gamma 0. I guess that was sort of a wasted step, right? Because right there, if I had not done that, it would have been delta minus P gamma 0. And that's what we're trying to show. We're trying to show that this is true. But for some reason, I distributed it in. And then I noticed that this gamma 0 is going to cancel the gamma 0 for each of the deltas, or each of the sigmas in P, and you're going to get with gamma I. And that's just sort of another, this is the proper form of it, so that's kind of interesting. And then if you factor out a gamma 0, you end up with this. And that factoring out is critical because gamma 0 inverse equals gamma 0, which is what allows you to factor it out so easily. So there we've demonstrated this interesting statement right here. All right, and what next? So then they basically give you these formulas. These are fun formulas, right? I can now use these relative reversion formulas to pull out all of these elementary physics quantities. You know, if I know the complex scalar form of M, so if M is written in this complex scalar form, I can do this relative reversion and pull out A. I can pull out E. I can pull out the pseudo vector and the vector. I can pull out, you know, the axials, the pseudo vector, the three pseudo vector type. So anyway, so these are some facts that we verified enough of these already. So, but it's a bunch of formulas that we probably won't be using much, but the point of all this is relative reversion is what's so critical in order to make this evident. All right, so in the next lesson, now we will get to Lorentz transformations in the next lesson. Commutator bracket and the Lorentz group and Lorentz transformations. That'll be a lot of fun, and I'll see you next time.